So you're building something that's meant to last. You've got literally thousands of types of stone to choose from. How in the world do you pick the right one? Well, it's not just about what looks good. It's about understanding a stone's entire life story. All right, so here's our game plan. We're going to start with the big problem architects always face. Then we'll dive into the 3 ways experts look at a stone: its biography, its resume, and its actual DNA. And finally, we'll see how it all comes together to find that perfect match. So first things first, the architect's dilemma. Why do we even need to get this deep into classifying stone? Well, because choosing the right one for the job is absolutely critical, and the stakes, they can be incredibly high. I mean, just think about it for a second. The stone you need for a massive skyscraper has to handle unbelievable pressure. The stone for your kitchen counter, that's got to stand up to spills, heat, you name it. And a historic monument, it needs to survive centuries of rain and wind. If you choose the wrong stone, you're looking at cracks, decay, maybe even total failure. But if you get it right, that stone can last for thousands of years. The secret to getting it right is all in the classification. Okay, so let's jump into our first lens, geology. This is all about the stone's origin story, how it was born. And believe me, that story tells you a ton about its basic character. This is always the first filter.
So all of geology, millions of years of it, can be boiled down to 3 main pathways. You've got igneous rocks, these are the tough guys, born from molten magma. Think super strong, super crystalline. Then there are sedimentary rocks, which are basically layers of sand and shells all squished together over eons. They can be a bit more porous. And finally, you have metamorphic rocks. These are stones that got a complete makeover from intense heat and pressure, giving them some really unique strengths and patterns. Right away, this origin story gives us our first big clue about what a stone can do.
All right, next up, the physical properties. If geology was the stone's biography, think of this part as its professional resume. This is where we look at the hard numbers, the performance specs that tell us if a stone is actually up for the job. You see, it's not just about looks. Architects have a really specific checklist. They need a uniform structure for predictable strength, and obviously no cracks that could be hidden weak spots. But, there are 2 measurable qualities that are especially important. Its density and how well it handles water. So the first big metric is something called specific gravity. It sounds technical, but it's really just a precise way to measure density. And why does that matter? Well, a denser stone has fewer little holes and gaps inside, which just makes it stronger and way more durable. It's like the difference between a sponge and a solid chunk of steel. And here's the magic number that engineers are always looking for, a specific gravity above 2.7. If a stone hits that number, it's considered top tier. It's got great internal strength, and it's suitable for almost any structural job you can throw at it. Now, let's talk about a stone's greatest enemy, water. A stone's porosity, its ability to soak up water, is a huge deal for its long-term survival. See, water gets into all those tiny pores, and if it freezes, it expands. And that process, freeze and thaw, slowly but surely breaks the stone apart from the inside. And because of that, there's a really strict benchmark. For a stone to be contender, its water absorption has to be less than 5% of its weight. Staying below that line is absolutely key to stopping that internal decay, especially if you're building in a place that gets cold winters. Okay, on to our final lens. We're going deep now, right down to the chemical level. We're talking about the stone's DNA. What it's actually made of determines its hardness and, maybe most importantly, how it's going to react to the world around it over decades and centuries. And what's wild is that most building stones fit into one of just 3 chemical families based on what mineral is in charge. You've got the silica-based stones, the clay-based ones, and the calcium-based ones. Let's see why that matters so much. Now, this is where it gets really practical. On one side, you have siliceous stones. Their main ingredient is silica, which is basically quartz. The way its molecules are bonded makes these stones incredibly tough and super resistant to chemicals. But on the other side, you have calcareous stones, which are built from calcium carbonate. Now, they can be stunning, think of marble, but they have a major kryptonite, acid. They react really easily with it, which makes them a terrible choice for a building's exterior in a city with acid rain. And that brings us to our third group, the argillaceous or clay-based stones. These guys have their own unique thing going on. The superfine layers of clay give them a special property. You can split them into these thin, strong sheets. And that's exactly why a stone like slate is the absolute king of roofing tiles and flooring. That specific trait is a huge advantage. Okay, phew. So we've got the origin story, we've got the professional resume, and we've got the chemical DNA. How do we pull all of that together to actually solve the architect's dilemma? Well, it really becomes a science, not just a guess. It's like a funnel. You start broad with the geological origin to get the general character you need, say something igneous for pure strength. Then you filter that group by physical specs to make sure it's dense and durable enough. And finally, you check its DNA to make sure it can survive in its new home. You apply these 3 lenses, and those thousands of choices get narrowed down to the perfect one. And when you get right down to it, this is the big takeaway. You're not just picking a pretty rock. You're choosing a material whose whole life story, from its fiery birth deep in the earth to its very molecular structure, makes it the one and only candidate for a specific job. Each of these classifications helps us read that story so we can make the right call. And all this kind of leaves us with a big question for the future, doesn't it? As our climate changes, as pollution levels shift, will the criteria for the perfect stone change too? You have to wonder, are the stones we've relied on for centuries still the right ones to build the cities of tomorrow? Understanding these principles is going to be more important than ever. Thanks for watching.